Yes, floor is yours, Kees Bos.
Okay, thank you, Eric, for the introduction. And of course, also thank you really a lot for giving me this opportunity to present our work on this platform. I think, yeah, it's quite an honor. So I hope you will not regret your choice, but I guess not. So we're going to talk about advanced through process modeling for microstructure evolution and mechanical properties in steel strip processing. And yeah, just to get started, I want to start very basic. I will assume that most people in the audience are familiar with this, but of course, quite central for our work is the relation between the steel microstructure and mechanical properties. So here, mechanical properties are illustrated by the classical tensile test. And of course, then we can have a look which microstructure elements have an effect on those mechanical properties. We start very simple composition. I think here we can all think of solid solution hardening that will increase your base strength level. Then the second component, quite important, is the grain size, or maybe the grain size distribution. I think also, of course, important. Then luckily in steel, we have all these different phases to play with: ferrite, retained austenite, martensite, bainite, cementite, which of course have a major impact on the mechanical properties. And as an added, say, degree of freedom in the design of steel with specific properties, we can also play with precipitates like niobium carbides or titanium carbides that can further enhance your properties. Now, of course, it's even more complicated than that, because it's not only the grain size, but we also have to often consider the crystallographic orientation of the grains, so the texture, which becomes very important if we want to look at the, say, the non-isotropic properties of steel. And of course, for many of the steel applications, things like a yield locus, so the behavior of the steel in different deformation directions becomes important. And we're talking about deformation, so then there is one other microstructure element that is important, which is not shown yet. That's of course the dislocation structure, which is interacting with all these microstructure elements like composition, grain size, grains, phases, and precipitates. So if we want to have a well-controlled steel product, we have to control the microstructure so that we can get good control over our mechanical properties. So then if we look at the steel production process, and this is then really specific for, or specific, but towards low carbon steel strip production, we have a lot of different process steps. And so the chain is quite long. So we start with casting. Then typically there will be a reheating furnace, and there might be some hot box in between to keep some temperature in the slab. Then there will be hot rolling steps like the roughing mill with some intermediate cooling and a finishing mill. Typical run-out table cooling, and then of course you have a coil which is still hot, which has to cool down. And this might be the end product for some customers, but of course we can also continue with some leveling and then pickling to get the oxide off, and which then can be continued with cold rolling and either batch or continuous annealing, after which there still might be a final temper rolling step. And then from a Tata Steel perspective, the steel goes to the customer, who again does forming operations on it. So it's a long chain where a lot is happening with your microstructure. So typical things here indicated that are changing. During reheating, you can think of precipitates that are dissolving, grain size is changing due to grain growth, etc. So if we list all the different phenomena that are happening, so we have precipitate dissolution, grain growth, and then during the rolling in the austenitic stage, we can have strain-induced precipitation. We'll have recrystallisation, which can also be dynamic or metadynamic, again, grain growth. And of course, because of the rolling, lots of work hardening happening. Then when we're cooling, the phase transformation becomes important, but also precipitation and ferrite can happen. And then these cold temperature deformations is of course all about work hardening. And then in the annealing lines, again, almost everything applies again. So I think this sets about the scope if you're talking about a through process model that has to describe the evolution of the microstructure and the mechanical properties. So it is a lot. And it also means that I will touch on many different topics during this presentation, but yeah, I think we can really show that we can connect all these different processes into one single through process and description. So if we want to do that, and we have to choose a modeling approach for that. And there are different types of models that have been developed and are in use in still industry. And this was already suggested I will talk about more than one type of model, but I want to start actually pretty basic, maybe also just to start a bit slow. But traditionally, we use mean field phenomenological through process models. These have been developed in the past, and actually we will see they're not, they can be quite successful. So what do we mean with that? So let's have a look. And for this, I want to zoom in on one part of what I just shown. That's the Austenite microstructure evolution during hot rolling. And just to give you some idea, I mean, here you see an image of the finishing mill in Muiden. And we have typical temperature conditions in the range of 850 to 1200 degrees. The strain per stand can be quite large, and also important is the strain rates can become very high. And you can have quite different interstand times. So that's the time before you reach the next deformation step. And these conditions, as you can also imagine, are of course not always easy to mimic in the laboratory. So in that sense, you need a good model if you want to extrapolate to these conditions. So, of course, what's really interesting for the microstructure evolution there is recrystallisation, and also important can be strain-induced precipitation. And yeah, what's typically used is what I call the Sellars model. And just to give you an impression, if you want to describe the crystallized fraction, you use an expression like this. So we have a very standard Johnson-Miller-Framey expression. I hope you recognize it in this form, where as a function of time, we calculate how much is recrystallized. And we see here this factor time 0.5, which is the time to 50% recrystallization. And how is this then described? Well, it's, of course, the equation is given here, and we see that there is some power law with the strain applied in the rolling stand, the initial austenite grain size, and of course the temperature comes back through this term here. And then just to illustrate how, for example, composition can be taken into account in this type of models, we see here that, for example, the activation energy can then be written as a summation of some base value, but also as a function of, for example, the manganese concentration. Of course, you can imagine this is just an example. There could be more chemistry terms included here. Then, of course, this is only part of the story, because you would also need to be able to describe the grain size, if only and because you have an illusion of a repetition of multiple rolling steps. And so you need to be able to calculate this initial grain size here from step to step. And again, we see a very similar expression. So the grain size after recrystallization given here is again some kind of power law function of the strain rate, in this case also included the initial grain size, the applied strain, and the temperature. And it is a mean field model, which also means we work with mean quantities. So if you only have incomplete recrystallization, so the fraction does not reach 100%, you apply a kind of averaging scheme so that again you have one average grain size for your next iteration. And then if you look at strain-induced precipitation, you will see something similar. So this is the famous Sellars equation, which says that the time for precipitation to start, or 5% of precipitation, is a function again of the applied strain. In the Z, there's again the strain rate and the temperature included. We have an activation energy, and here you see the Ks, which is the niobium carbon nitride solubility product, and of course you see the niobium concentration playing a role there directly as well. Now, this is just to give you an idea of what type of equations is traditionally being used, and they have something in common, and that is that we see a direct correlation between process or deformation conditions like the strain rate, and the temperature. And it works on averages, average grain size, and the average composition. And actually, these models have been really widely used. And if you have a look in literature, the group from Professor Militzer has published models for HSLA grades, for carbon manganese grades, but also for more modern trip steel grades. So actually this can work quite all right. And of course, also there's been extensions, for example, the work from Spain to extend it into grain size distributions. Now you might wonder, this all seems fairly basic, so how well could that work? And I do want to share that with you. So here from our own work, we have an example of how we describe the mechanical properties with such a model for niobium HSLA grades. And what you see here in these three graphs is the measured tensile strength, the yield strength, tensile strength in a uniform elongation, plotted versus the model prediction from such a mean field phenomenological model. And this is then after fitting against test house data. You can imagine that at the steel plant, like in Muiden, we generate lots of tensile test results. So this is nice data you can use for that purpose. And it turns out that the tensile strength, for example, you can predict quite reasonably accurate within a standard deviation of around 9 megapascal, which for many purposes is really good enough. Of course, then you might ask, well, how representative is a test that you take typically either at the tail or the head of a coil? Well, that's quite interesting, because a model that has only been fitted against data from such tail or head samples actually turns out to be still representative for the entire behavior of the coil. Because here we have process data that might be varying over the coil length. We can also put that in the model. Then here you see an example in the blue line of the predicted tensile strength for a specific coil, which also went over a temper mill. And you can imagine then that the roll force that you need to apply in a temper mill is also being measured. And this gives then quite a good measure of the strength of the material. And you really see that the profile is fitting quite well with the prediction of the variation in properties over the length. So I think it sets a kind of baseline. So if we summarize these classical models, as I mentioned before, we have this direct relation. So it's not really a physical model which links to, say, material state or material properties. But nevertheless, if properly tuned, it can give very reasonable results. But it does require quite some testing data for the model calibration. So this is, as I said, the baseline. So now if we want to do anything else or better, this is what we have to beat. And in some situations, it's already quite accurate. And so then I think we can go in two different directions. And so we can either go into direction, well, no, we want to have, say, more full field, really physical based through process models, or we can go in the direction of data models. Given the title of my talk, I hope you're not surprised that here I will focus on the full field physical models. Which then brings me to introduction of the DENSE program that I think Erik already briefly mentioned. So that is what is called the digitally enhanced new steel product development. And I want to share the concept of that with you. So what is the idea? So we start here in the middle with a also RVE based or representative volume element based microstructure evolution model, which feeds into micromechanical models like crystal plasticity, which then can also give data to, say, more macroscopic modeling. And the idea is that this is all full field physical models that we apply here. And of course, we know that these models, although they're physical, they still have parameters. So they will need calibration data to tune some of the parameters like a mobility or nucleation parameters, hardening laws. So the idea is that we couple that with, say, small scale, high throughput testing facilities. And then once we have that, we have an offline physical model description that we can feed into a kind of digital environment of the production environment, which means that we create a kind of digital twin, which has a very good description of the material behavior, which we can then also mimic in online control. And maybe for online control, we can use, again, then better calibrated, less sophisticated models, but it should really help to, during the production, or sorry, the design phase of the new steel products or the development phase, to have much faster, of much higher success rate if it comes to translating the recipes that we developed in the laboratory to the full factory scale. And this really was a big program. And so we started this, I think, of course, the initiative came from Tata Steel, but we found many partners. And in the end, we had over 15 PhD and postdoc projects working mainly on developing these physical models here. And that's, of course, what I want to show you some highlights from. And yeah, let's get started with that. So that brings me to the more or less the second part of my presentation, the full field physical through process model. And I'll start with a brief overview to give you some feeling for how we connect all these parts that are in there. And then for a DP1000 steel grade, so a dual phase 1000, I will show how good these models are working. So this is a very short schematic description of our through process model platform, and it's of course, but it's a modular setup. I hope you recognize the production steps that I showed earlier. And so we still have something for reheating in the furnace. Then we have the rolling stands and time in between, which repeats for all the different rolling steps that we had. Runout table, cooling and cooling on the coil, cold rolling, continuous annealing line, and during application. And then here below, you see the type of model that we want to apply there. And you see everywhere in red where we essentially have a microstructure evolution step. We have a written CASIPT, which is a cellular automata model for microstructure evolution calculations. And then for deformation, the idea was that we are more open, so we could, where necessary, apply crystal plasticity either through Damask or finite element modeling, but also we could use non-topological models like full constraint Taylor or the LML model. And the way that we stitch all this together, that we connect the in and outputs of these different models, is that we have a Python framework, which really allows us to connect all these things in a very efficient way, and also in such a modular way that we can easily exchange them. So you see that this CASIPT model plays quite a central role, and I think that's what Eric alluded to when he said that we a long time ago started this CA model. So I want to spend a little bit of time to introduce this CASIPT framework to you. And so CASIPT stands for Cellular Automata Sharp Interface Phase Transformation Model. Well, the name is not that exact because it goes beyond phase transformations, but it is a full field model of microstructures. And so we have different submodels, for example, Austenite decomposition, but also for recrystallisation. And here in 2D, here you see a very brief example of the Austenite to ferrite transformation, but this is just to give you already some feeling for how such a model works, or actually what the typical output of such a model could be. So how does it work? Well, as any CA model, we have a grid of cells with a finite number of states, and we have to define a set of rules that define the evolution of those cells. And it's important to realize that the state of the cell in the next time step or next generation depends on its current state and the state of all its neighboring cells. And then in CASIPT, the state is its thermodynamic state. So which phase is it, or in which orientation does it have? And of course, also things like concentration of carbon or other elements could be considered. And I think quite important is that on top of that, we have a finite difference method which directly works on the CA grid that can be used for diffusion calculations. So in that sense, it's not a pure CA model, but it's a combination of a CA and a finite difference model. Then to keep the model efficient, we essentially track the interface. So we only describe growth happening at interfaces. And for this, we track of these interface cells the growth length. And you see here an illustration how we do this. So initially, we only consider isotropic growth, and just every time step we update the growth length of every interface cell based on the interface velocity, and the interface is then typically described as a product of the mobility and the driving force. And this driving force could be from recrystallisation or for phase transformation. And so in that sense, this is quite basic, but already quite flexible, and it means you have a quick way to introduce many different type of transformations into the same framework. Then we come to the DP1000 example, and at DP1000, as you can imagine, is quite a complex steel product. And you see here an example microstructure, which contains 10% of martensite and about 47% of ferrite and 43% of bainite. But during the design of this grade, lots of different strategies were tried. So this is then with 3 phases, but also purely bainite or martensite might give a reasonable DP1000. You could also include retained austenite. You can play with microing elements that might also be needed to obtain the optimal properties. So the idea to use this grade as an example is to show that with the models that we have, we feel that we can really handle make a useful contribution to development of advanced and also ultra high strength steel development. So it should be challenging. That's the idea. I mean, so let's have a look then what we get if we look at this process chain again. And then we start here, so with the reheating furnace and the roughing mill and the finishing mill. And what I show here as example output is extremely basic. It just shows for the 7 stands that we have in our finishing mill, the fraction recrystallized as predicted by the model. And what do we see? Well, initially, the first 2 stands, we have full recrystallization, and then we have partial recrystallization. Of course, this is not for a 3D model a nice output, of course, so we can also have a look at the 3D microstructure. So this is then the microstructure at the end of the finishing mill. And in the bright orange, we see the recrystallized ferrite and still deformed, austenite and inductee, which of course matched with the strain map. And actually, I think this is something important that we have to point out why, especially for advanced high strength steels, and this type of full field modeling becomes interesting and important, because we see that recrystallization is not complete, and this is a bit typical for these heavily or more heavily alloyed grades where we have higher levels of manganese or also of other substitutional alloying elements, which means that typically recrystallization goes slower. So if you look at a typical recrystallization curve, and here the scale on time is a bit arbitrary, but say for more traditional grades, you would almost always be in this full recrystallization scheme, or if you have heavy precipitation, it would actually be no recrystallization, which means that if you make a prediction, then you don't have to be that accurate as long as you somewhat reasonably predict that it is fully recrystallized. But here you see that we are straight in this part where the change can be quite big. So if you're now off in your prediction a little bit, it can have a big impact on the microstructure that you are predicting. And so this shows that for these more modern steel grades, we actually need more accurate modeling tools to keep correct predictions. Now, of course, I have to say a little bit more on the model that we're applying. So what you see here is results based on strain-induced boundary migration as the nucleation mechanism for the recrystallization model. And we have been working within this dense program to develop that further. And it's work from Pablo Garcia Chao, who did an experimental study in an iron nickel alloy, and there it shows actually that the strain-induced boundary mechanism nucleation seems to overestimate the amount of nuclei being formed. So it looks that we have to improve this nucleation description by looking more into the transition of low-angle subgrain boundaries into high-angle subgrain boundaries. So that is a work in progress, which I think is important to mention. Also something that I cannot show in the limited time that I have, but we also developed a hybrid model with Damask, so where we describe the rolling deformation with CASIPT. So we actually can also describe dynamic recrystallization. Of course, as we use Damask, then these calculations become quite intensive. So yes, we can do it, but it's still a challenging task computationally. And something also that I want to mention is that, of course, here in the reheating stage, where the precipitates that might be present will be dissolving, we can make a nice connection to improvements that Rutger Sloter made in his PhD work using a mean field theory, which can use gives us a very efficient way to calculate which precipitates might still be present after the furnace reheating. Okay, that brings me to the next process step. That's the runout table cooling. And so we cool here typically from, say, a finishing temperature of around 900 degrees in the order of 10-20 seconds to the coiling temperature, which is often somewhere between 600 or 700 degrees. And then, of course, on the coil, it will cool down more slowly to give it a bit more time for phase transformation. Now, for the model here, what we would like to see is that and the austenite grain size that we inherit from this previous step, and also any remaining strain, should have its impact on the ferrite grain size that is predicted by the phase transformation model. Also, and segregation effects, because of the higher alloying content in manganese, typically can lead to bending in these grades. So that's something that we also want to be able to describe and predict. And important is that we can use orientations to predict the transformation texture, but I will get back to that. So just to illustrate then what the microstructure looks like. So here you see in blue then the ferrite, and in gray the pearlite. Of course, if you then look at the carbon map, the pearlite is high in carbon, and here already you see some example of the as an inverse pole figure coloring of the ferrite grains. But let's look a little bit more in detail of this phase transformation model, because I think it's important that we show the level of sophistication that we actually managed to reach in this model description. And I want to look at the bending due to segregation effects first, because this is a nice example of how such a full field model can take local effects into account. And so if we here have a, perhaps not really typical, but a DP microstructure, and you see here something strange. What that actually is where a line scan was done to measure the concentration profile. So what do we see along this line? Here we see here in red the manganese concentration, which on average is something like 2 weight%. But we see here at the center line that we have concentration reaching almost up to 3 weight%. And if we look at the chromium in dark blue and the aluminum levels in light blue, we see that they're also scattering quite a lot. And so center line segregation, but for sure also secondary dendrite arm segregation, so microsegregation can play quite a role. It can be quite expensive. You have variations up to almost half a weight% of manganese effectively, which will of course have an effect on the microstructure evolution and gives you this banded structure. So the goal then is to predict the measure of bending as function of the composition, and of course then the runout table, but later also the continuous annealing line time temperature path. So what do we need for that? How can we achieve that? And of course, the first thing you need to do is to add in this case, manganese concentration profile to your simulation setup. And well, that's something that can be done. And then for growth, you have to make the driving force a function of these local manganese and carbon concentrations. But the important part is actually that you need a proper nucleation model that can handle this. So then we get to the I would say almost a classical nucleation equation, here described in the form as I think given by Erik Offerman, where the psi factor is handling the shape and boundary energies of the nucleus, and here we have the chemical driving force. Now we can actually simplify this equation a little bit by saying, well, this driving force probably can be written as this linear product of some 4 prefactor times the undercooling, and which means that we can actually combine then the psi here with the psi to give us one lambda value that's is a kind of nucleation activation energy. And then this A3 temperature is the temperature that takes the local composition into account, which we will mimic by setting a manganese concentration profile. But in essence, you want to have a profile in the A3 temperature. Now, this is a nucleation rate. In the CA model, we interpret that as the chance that a potential nucleation site becomes active in a single time step. And as you will see here, with this model, we can really make interesting predictions. So here we see 2 simulation results. One is for a low cooling rate and one is for a high cooling rate. On top, we see the grains and phases. So in orange, again, the austenite, and in blue, the ferrite. And below, we see the carbon concentration map. And what you see is that for a low cooling rate, we get, first of all, larger grains, which is also what we would expect as a function of the cooling rate. But also we see that the structure is much more banded than in the situation of the high cooling rate. And by just putting in these fairly simple rules, you can really mimic this behavior, because it is, of course, in the low manganese regions here, and nuclei will form first, and because you have a low cooling rate, they have quite some time to grow, which means that the carbon concentration in the high manganese regions go up further, which means that there will be no further nucleation in those high manganese regions anymore, which is of course not true for the high cooling rate. And so I think this really shows how powerful this method actually is in producing relevant microstructures that have a real impact on the mechanical properties. But we have to go in the end one level deeper, and then we come into the orientation-based nucleation and growth model. And so this is work from Jesus Galan Lopez, and he really made a huge improvement to the CASIPT model by introducing orientations to essentially any model. But so how do these orientations then play a role? I mean, here you see just an example of grains colored again by IPF. It's not really from a phase transformation, as some of you might recognize. And we have two options. We can assign orientations per grain or per cell. In most situations, it's good enough to do it on a grain basis. And what does this gain you? First of all, it allows the calculation of the misorientation angle and boundaries. And that means that you can make a differentiation of nucleation sites based on boundary energy. So if you have austenite grain boundaries which are of low angle character, and you will see that there's less nucleation there. In the end, we do have somewhat limited resolution in our CA model, so we cannot fully resolve the interface, so we are limited to this misorientation angle only. But that also is good enough to introduce selection rules for the orientation of a nucleus. Also from previous work, it's known that if you go from austenite to ferrite or the other way around, you will often see one or even more Kudryavov-Sachs orientation relationships with your nucleus and the parent grains around it. And so if you would have a triple point where 3 austenite grains meet, you could even have more than one KS relation with some of these parent grains. And we use these selection rules to set the ferrite nucleus, so orientation. So the nucleus orientation is selected by choosing the best fit with the neighboring austenite grains. And I think this illustrates it best. So here, what Jesus did is that he generated 3 different austenite textures: a random texture, a cube texture, and a beta fiber texture, just to illustrate the impact of the parent orientation distribution. And then for 3 different system sizes, you see the resulting ferrite ODF. So for a random austenite distribution, you see as you progress into larger grain sizes, also a fairly random texture coming back. And for the beta fiber and the cube, I think you can really see the impact of the parent austenite ODF. And what you also see, of course, is that you do need proper grain statistics. So if you have a small system, you will only have a limited number of grains in your system. And so for a proper texture description, that's simply not enough. But luckily we can handle this type of system sizes because the CASIPT simulations are fairly efficient. It's also to do with the way that Jesus managed to implement these orientations into the model. So I think we made a big step forward, and you can also imagine that being able to predict proper transformation textures is also quite important if you want to do crystal plasticity modeling of your mechanical properties afterwards. And as we're not only limited to ferrite as a product phase, and of course, if you talk about Bainite and martensite, then the orientations also are essential to describe those product phases correctly. So this has been a huge contribution to the CASIPT model. That brings us to the next step in the process. So that is the cold rolling step. And here, again, we have, as shown in the schematic, we have different options. So we could use the VPSC model, or full constraint Taylor or Alamel. So these are non-topological models, and the idea is that so you generate a deformation texture, and this is a typical cold roll texture, of course, which we can then actually, on a statistical basis, map back on our CA microstructure. Now, you will see that this is actually not the mapping belonging to this one, but I think it illustrates the way we can do it. So of course, it means that we can do a fairly efficient non-topological model calculation if we want to be able to run this entire scheme within a reasonable calculation time. But if needed, we can also do a crystal plasticity calculation. This has been made available by the work from Caro Sediriani, which was not really part of DENS, but in a related project, it was made available in Damasti's large train simulations. And I think that's also, again, quite beautiful work, but it shows the resolution that we can gain in the description of the deformed microstructure. And this, especially for formable steels, is of course a very important input then if you want to model the ferrite recrystallization. And it also shows that quite often you have to make an important choice. Do you want to change or exchange accuracy for simulation time? And it will depend on what you really want to describe in the end, what you need. So then we get the continuous annealing step, which is shown for as a typical example here. So quite rapid initial heating, and then we get into either intercritical annealing or full austenitization. And then on cooling down again, the austenite will transform into ferrite and or bainite and or martensite. And here some typical output for this DP1000 cycle. So we see complicated microstructure. In blue still the ferrite, in orange some retained austenite, in green we have the bainite, and we also see some martensite being formed. And of course, this is the final result, but from the simulations you can get all intermediate phases. So if you really want to know that this was intercritical annealing, you can no, it was full annealing actually, because you see here that the austenite phase fraction reaches 100%, and then on cooling the ferrite starts to form again, and we have a major bainite phase, and at the very final quench we have some martensite forming. And the bainite is an extremely important phase for these advanced high-strength steels. So maybe traditionally of a dual phase steel, you would think that's ferrite and martensite, but yeah, it turns out that to apply bainite in these products is really helpful to get good properties. But it does mean that we had to add a bainite model to our phase transfer, to our CASIPT model. Just before I get to that Bainite model, I do want to show then how good are we able to reproduce. So here we see the phase fractions as predicted by the CASIPT model, and this for this specific cycle, the experimentally observed phase fractions are, as you see, quite close to this. So that's quite encouraging that it shows that we can really describe this to good with good accuracy. But to get to the Bainite model, so this is work from Arthur Nishikawa, who I think did a great job in developing a Bainite model which is still practical, also in terms of calculation efficiency. So what he does is he describes Bainite as a pseudo phase, where initially we ignore the thickening and widening of the Bainite blocks. And of course, we can no longer apply this isotropic growth rule because it is directional, and we need the orientations to know in which direction it is growing more faster. So Arthur developed an off-center capture rule, which is illustrated here. And so as soon as the interface moves into a different cell, that entire cell is being considered as being transformed. And of course, we need still a description for the velocity of the interface, and that's then based on the diffusional approach developed by Leach, where still important is that the Bainite growth velocity remains a function of the carbon content ahead of the growing interface. So if you have previous ferrite formation, which locally increases the carbon concentration there, it will affect how Bainite is growing there. And we see a similar expression for the nucleation rate as we saw for the ferrite, but of course now we no longer have the A3 temperature, but we can use the Bainite start temperature, for example, with the work from Van Bohemen there. And for the calculation then of these interface concentrations, we do this under par equilibrium. But yeah, just to give you then a 2D example of what that looks like in practice. So I think we have a very convincing and good description of the Bainite morphology. And in terms of kinetics, we're also able to describe a lot of things already correctly. So that's very encouraging. So that brings me back to so we were finished with the continuous annealing part. And of course, then the next step is to reach the mechanical properties. And this we do in Damask, and there mainly we use the phenomenological or crystal plasticity, but we did a few important the changes or tweaks there is that we're able to take the composition into account by changing the hardening parameters more or less automatically, which means that if you add manganese, you do want to have your ferrite to become stronger. The carbon in martensite should have a direct effect on the strength of martensite. And then typically what you want to do is that you want to do a tensile test simulation in different directions so that you can really assess the anisotropy of your material. And a very interesting addition based on the work from Fahid Rezazadi from Eindhoven is that we can also look at some damage evolution, which means that we can look at the global versus the local ductility, which gives us an impression on application performance like hole expansion capacity. And so that shows that we can even use these methods to go beyond just tensile testing, but really get into the realm of application performance. Of course, here just an example of the input for Damask. So these are the per phase hardening laws. So we see the softest phase is ferrite and Bainite, for which the uncertainty is still the largest, I would say, for this type of crystal plasticity work. And then the martensite hardening curve. And a typical output would be something like this. And so we obtain a tensile curve from which we get the typical tensile properties like yield strength and the tensile strength. Of course, if you do a full field simulation, then just showing a tensile curve is not that exciting. And so, of course, we can have a look at the in detail the response. So here on top, we see the strain distribution as the tensile test is progressing. And here you see the stress distribution. Where of course, stresses will be higher in the Bainite and martensite phases. And then the ferrite will take most of the strain. But I think this actually is the most exciting picture here, because this is then the post-evaluation where as a kind of post-processing step, we can have a look at the triaxiality of the stress state, which is a good estimate for the initiation of damage, which gives us this estimation of the local ductility. And if we then have a look, how well are we able to reproduce the properties of this grade? So then we see here the Damask results, and these are the experimental results. And it's not perfect, but especially given the uncertainty we still have in the Bainite hardening, I think we can already be quite happy with these results. So this was for, before continuing here, I want to point out one more work from the Dance group, and that's the work from Lai Liu, actually, who goes beyond this phenomenological law modeling for the martensite behavior. So he introduced a different concept for modeling martensite, which also is then connected to a damage model. So there we can go into an even more physical description that unfortunately, I simply do not have the time to, there will be a presentation by itself. I just wanted to let you know that there is even more fundamental work going on in that direction. Of course, it's now interesting if we have this model to see, well, can we make some predictions if we do things differently? So here we have in blue our original cycle. And then here we have a few other annealing cycles for which we, in the laboratory, looked at the properties. And the nice thing is that this through process model is fully scripted. So in essence, we can effortlessly put in any combination of times and temperatures. The only thing is, yeah, the mass calculations in the end of the properties, they take some time, and compared with that, the microstructure evolution part is almost negligible. Now, what do we see then? I mean, it's too many variations to show all of them. So if we just look at the impact here, and this is what we call the slow cool temperature. So if we reduce that temperature from initially 700 degrees to 650 and 600, we see that the model predicts actually that the amount of ferrite being formed goes up at the cost of initially some bainite, and then at the lowest temperature, we also see that a lot more martensite is being formed. Now, if we then look at the experimental results on that, we see that it's initially follows quite well, but then you see that we predict much more ferrite for the 600 degrees temperature as compared to what we measure. So we do have some tuning of our model parameters to do, which actually is also a bit of a challenge that I will come back to later. And we do have a feeling that the Bainite model might be responsible for this. So Arthur already had some ideas to improve the Bainite model that I do want to share with you. And the idea is that we have to include the lath thickening and widening that we didn't do so far. And then as the phases of the lath plate are relaxed by diffusional mechanism, which you can call the second stage of the Bainite reaction. And the rate of those phases should be controlled by the rate of the eutectoid decomposition. And yeah, that leads to a rather different growth law, which is quite, oh, I think I have to switch off the pointer too. No. Oh. Yeah. Yeah, now I can show the, sorry for that. And so you see here, now that we have initial fast growth, which is continuing, and then slowly you see the broadening of the plates, which I think is indeed a more realistic description of the growth of Bainite. So then if we look overall, what does that mean? And so now initially you will see that there is some untransformed austenite after the hard impingement of the bainitic ferrite laths being formed. And then the lath thickening results in the completion of the transformation. And then I want to follow the work of Ian to describe the second stage, which then either could lead to upper bainite or lower bainite. But it's, yeah, we still have some open questions there on how to do this properly. So that's something, it's a bit work in progress, but I think it's very promising and a good improvement again on the Bainite model. So we hope that with this improvements, we can even further and improve the accuracy of the predictions. But to get back to the property predictions, and so and we had these different cycles. Then here in this image, you see some of the key numbers. So I show in on this axis the tensile strength for the different slow cool temperatures, and you see that for the lowest temperature we have quite a low tensile strength, and then if you look in the response in terms of formability, we see that this low strength translates into a high AG, so that's the uniform elongation. But actually, if you look at the local ductility, so that's your heck performance, we see that this is not really improving. And so if we look at the numbers, we see it here, and you might wonder, well, we lose a lot of strength, so why are we not rewarded also with a better local ductility? And that's of course because here we now have introduced much more martensite into our microstructure, where the phase contrast between martensite and ferrite is much larger, and this is quite well known that this is quite bad for things like heck or edge ductility. So I think it shows that this type of analysis that we can do on the microstructure and the mechanical response is really interesting and a really powerful tool to judge which microstructure behaves in which way. So that more or less brings me to the end of my presentation. And so I mentioned these different types of models developed and in use in steel industry. And I think if we summarize the 3D full field physical through process model, I hope I've convinced you that we can really reproduce complex microstructures and mechanical properties. As I indicated, some of the model parameter identification is a bit of a challenge, and which parameters we have to think about them. Well, these I mentioned mobilities, but also hardening parameters. And these models are not extremely slow, but also not extremely fast. So to find a good fitting procedure for these type of models is not so easy. And also to have a lot of reliable experimental data, just quantifying these complex microstructures is also quite a challenge. So there, I think we still have to improve somewhat. And that's also why I write that for the calibration, we really need high quality experimental data. Of course, I mentioned data modeling as a different path, but I think the real promise is if we go into hybrid data physical modeling, and there you have to think, hey, maybe some of the CASIPT and the Damask work can be captured by meta models that are based on machine learning, which could really help to reduce these calculation times for these models. So that might also make the parameter identification much more easy. And of course, some of the fine tuning might be able to benefit from huge quantities of less accurate data coming from the mill as well. So I think this is also an exciting new path to develop these models further. And that leads me to the final slides with all the people who have contributed to this work. Here I list all the postdoc and PhD students. All the supervisors of them from the university side are of course also acknowledged, but it simply didn't fit anymore. It's not all of them, but it's mainly a large group of here seen here, and also a few people from Tata Steel I want to acknowledge. So leads me to my final slide. Thank you.
Thank you very much, Kees Bos from Tata Steel in Eemhuizen, the Netherlands. Very nice presentation, impressive work. Let me stop the recording now.